Hello everybody, welcome to another stream. How are you all doing? How are you all doing? So last stream we got the occupation map created, which means we can now know all the neighboring clusters with a simple with two texture lookups. We can see if a cluster is completely surrounded by another cluster. So now we can simplify the tree by using this new shader called the Refine LOD shader, which we wrote up some streams ago. So in today's stream we'll get this one up and running, this Refine LOD, which basically we launch one of these for every... No, we just launch one of them. And it's going to start at the leaf nodes of the tree and go up the tree and generate all the lower level of detail, right? So let's just get this boy plugged in and BC equals 0 initialize, bam. So this is the last one we wrote, was down sample occupation, and here's this Refine LOD, which launched this thing once. I think we might need to use indirect, because we need the GPU to tell us how many leaf nodes there are, and that will tell us how many... Yeah. So that's the shader we're launching. This enum is generated by the compiler, so we just fill it in with the name of the shader. There we go. Oof. We'll store the indirect args in the buffer. So I'm curious. So just be in the global buffer. This is globally accessible to every single shader. So this is the Refine LOD indirect args. So for this one, the X needs to be the number of leaf nodes, and then the Y needs to be the number of... Wait, is it the same? No, it's slightly different. Yes, the X is children. So we just dispatch along the Y. Sorry, so the X would be... So 8 threads... So there's 8 threads going across the X in the local, and then 4 going across the Y, and that's the cluster node. So we need to make sure that we divide that by 4, basically. Number of leaf nodes divided by 4, so that's the number of groups we need to launch. Sweet, so then that would mean... when we launch it, here, use that one. Okay, so we just got to fill in these arguments now, and then we can go over the shader and make sure it's all correct. Let's get that again. So it needs to be able to read write to cluster nodes. I've done that in the past, isn't it? There it is. Okay, rewrite to cluster nodes. We need to read from the child indices. There's a free list, so we need rewrite access to. Sphere free list. And then the cluster occupation map. This should probably be prefixed as spheres free index with this. Maybe not. But yeah, we want like a base ID. That's all we want. So this needs to be here. It is base ID. So we use it here in the shader, which we're going to go over this code in a minute, but we add the LOD. Is that right? No, it might need to be the other way around because that's a MIP. Yeah, we'll look into that and fix that. We add the LODs to the base ID, and then that gets us our texture. Since our textures are, or the MIP textures are in their IDs are allocated sequentially. And in the shader, we can just load from that texture at that MIP. So yeah, I think we just need to do the sync code now. So let's get all that in there. Should be pretty simple. So it's read write, read only on the child indices. To be honest, it probably doesn't matter if they're all read write in this case because they're read write, but I don't know. I didn't change this one. Spheres buffer ID, that's it. Oh yeah. So that's all the sync code. That's read only. The occupation thing. Base ID. That's read only. And there we go. Amazing. So now this, if we were just to launch this, it will probably crash. So what we want to make sure is that it actually works. So we can go over the shader and line by line and make sure it all works basically. Okay. So this refine LOD, what does it do? Well, you've made your level of detail tree of clusters. So we've done this already. We've got, so the first level of detail, or the lowest level of detail, is one cluster. 2 by 2 by 2 of spheres, and each sphere can have a child cluster in the next level of detail, and so on and so forth, right? So the next one has, so the first one has 1 in 3 dimensions. This one will have up to 8, right? Because it's basically an octree. And then there'll be L2 would be 64, and so on, right? But yeah, they'll have up to 64 in L2. But some simply might stop here, for instance. So we've got this cluster tree which has a bunch of nodes, and so there's leaf nodes where they just end there and they don't have any children. But there's also leaf spheres where this one can have a child, right? This is not a leaf sphere because it points to the next one, right? And technically this will not have a sphere here yet because this is a lower level of detail sphere based on all of the spheres which sit inside this thing, right? And then this, but this is a leaf sphere because it doesn't have a child, right? So the job of this shader is to start off on all the leaf nodes. If they all have spheres, it will see if there is a neighboring cluster in 3-dimensional space on each. If it's completely surrounded by clusters of spheres, and if it is, then we will say, okay, well, we don't need this level of detail anymore. We're going to replace it with one in the lower level, right? And then get rid of this node entirely. And then we just go up the tree and say that, hey, we've finished this guy. And until all of the threads have come by and said they've finished this guy, the last one to get there inside a cluster will then begin the process again, where it checks the neighboring cells or check the neighboring clusters in 3-dimensional space and see if they're completely surrounded. And if they are, it will it will simplify. So that's all this shader does, but it's very easy to mess up. So let's just double check. So your leaf node index is the y, dispatch index y. Your cluster index is local index. Why does that make any sense? Yeah, got it. Your child index is the x, yep, because there's so many children. Here's a little children bit mask, so when we check the bit set, we can just use this. It just picks up the lower 8 bits because there's 8 children, and we use the higher 8 bits for something else. We get the number of leaf nodes. We check to see if we're outside the number of leaf nodes, and if so, we return. That all makes sense. We get the midpoint cursor. The midpoint cursor is basically to do with how we handle the nodes. Here's the midpoint cursor. On the left-hand side, this in the array, this is all filled with the leaf nodes. On the right-hand side, this is all filled with the non-leaf nodes. There's less non-leaf nodes than there is leaf nodes. So that's what the midpoint cursor is. I just realized that I think my the constants are messed up. Yeah, let me fix that. Yeah, because I was trying to do it as like, so it would be a multiple of a meter, but then it's not really worked out too well when we do our LODs. So not a good idea. So I'm just fixing these constants so they're proper. I think this one makes sense. Let's double check this. So it's basically going over all the 2 to the power of index and it's summing it all. Cubed, right? So it'd be 1 cubed plus 2 cubed. Let's write these down quick. 1, oh my days, 1. Huh? Why is it doing that on bloody enter? 8. Yeah, so 3 cubed. Oh no, that messed up. 27. 4 cubed. 4. 5 cubed. And then 6 cubed. That's wrong. I'm doing it wrong. Damn it. Right, that's definitely 8. So 1 shift left. Yeah, then 2 cubed. Yes, there's. Right. 1 shift left, 3 cubed. 5, 12. I missed 64. Okay. 1 shift left. 5. Did I do 16 cubed? Yeah, okay, 16 cubed is the next one. And then we want to do 32 cubed. 7, 6, 8. How many of these we got? LOD 0, 1, 2, 3, 4, 5. Do we need one more? That was 32, wasn't it? 64. I don't know we need this one, but let me just double check before we commit to it. So what do we need to sum up to do the non-leaf nodes again? The other ones before. LOD 0, 1, 2, 3, 4, 5, 6. And you got 8. Something's a bit... because clusters are Yeah, because on LOD 0 you've got one cluster. LOD 2 you got 8 clusters. I think, yeah, this makes sense. 0, 1, 2, 3, 4, 5, 6. And then 7 is the final one. Is that right? That was 64, wasn't it? Yeah. Then 128 would be the, yeah. Okay, so we've got to sum all these guys up. Right, so 32, 7, 6, 8, add that. 9, 6, add that. 5, 12, add that. 64, add that. 8, add. 1, add. There you go. Okay, that is the right number. That's good to know. Excellent. So now that those are corrected, we can move back to where we were on the shaders. Okay, so midpoint cursor, which we went over. Our node index is negative leaf node because if you have a leaf node index, yeah, leaf nodes are in the negative, right? Get the min-max bounds. If you're outside the min-max bounds, return. Some nice safety checks in there. And nothing was wrong with those. It's fine. To get our absolute index by adding to the midpoint cursor, and then index and get our node. I'm curious, since we put the safety check here, I'm guessing there's a safety check down here. Unless we've already checked it before, something like that. Anyway. Okay, so the job is to check to see if we yeah, so we set up the LDS. So wait a minute, do we write these back? Oh, we write them back in, isn't it? Interesting. Yes, we clear these out in the LDS. So we set the spheres count to 0 and we clear out all the spheres. Right, we'll see how that's used in a bit. So here's the children bit set, so each cluster can tell us which if they have any child nodes. So we saw on the leaf nodes, obviously they will not have any children. So on the first lap round, this is going to be a 0. What's this children bounds? Right, here's the safety check. So we get the child index out. Check if it's in bounds. Right, that's all code, that's good. Okay, so we have a child here, and it's in bounds. There's the safety check. We get the absolute child index and grab the node. Then we only try and simplify. Yeah, so what we have, let's go back to this one. So at this point we have this guy, right? We're in this whole sort of like node, and each thread has its own sphere, and they're checking their child node and seeing if they have a full set of spheres in here, and if they do, then it's gonna try and create a lower LOD sphere. So we use the LDS to see if it is new. What are we doing? So if each thread has a so you have 8 threads which have the same node within a wave of 32 threads, and then you've got 8 so there's, and each of those 8 threads have their own child that they're looking at, right? Right. Okay. Yeah, I was wondering if I could do this a different way. Yeah, because the problem with this approach is you can't simplify the material. Because well, you can, you just have to for loop over it. But maybe instead you can do it from the other approach, you're at this sphere, or you're at this node, and when you're doing your node, you can check the spheres, and then you go and poke in there the lower LOD sphere if you can. But then I think in the future, I might want to try and replace these with ellipses in this sort of space, because right now they're just spheres, so I can get some. So maybe it is better if we do it from this, and this one uses 8 threads to check simultaneously the nodes and if they're full, because maybe we can use it to, we can use a bit pattern to tell what ellipse to use instead, or something like that. Yeah, I think this is the approach we should go with. Okay, anyway, so we carry on. So yeah, if the child node has a full set of spheres, we create the lower LOD sphere. So it's always going to be new, right? So that's just gonna increment by 1 every time. That's just copy paste code for some other place. The material index, we need to sort this out. We just pick the first sphere's material index in the child, and use that one. This is not a problem we're trying to solve yet, because we haven't done any of that code yet. We're just trying to get the clustering system to work. Then we create our sphere, create an LDS temporarily, because we don't know how many. Wait, why do we do that? Yeah, because we don't know if we're going to actually have any spheres at all at this point. So we put them into LDS, and then we're going to copy them. We're going to allocate an array, and then put them in there. So, yeah, I think this is legit. Try to move the child if it is a leaf node and is completely surrounded by other clusters. So this is a complete, like, hyper-optimized way of checking our neighbors, right? We've got this occupation map where each bit in the bit set is a cluster, and then we repeat information within a bit set. So we only have to do a couple of samples. It's pretty. Anyway, we've been over that in the previous streams. Let's just make sure. So we say if the child node, if that bit set, yeah, so if it doesn't have any children, excellent. So we get the position of the current node. The current node? Are we doing that wrong? That should be the child node, right? Because you're checking. Yeah, that child node is completely surrounded. Yeah. But it's not the right LOD, right? We need to be checking at the LOD of the child. That's right. So get the cluster cord, get the bit coordinate, add one for the 1-bit empty border. So we can check with our if statements. And so our center sample point is surrounded by bits within the bit set. Within a bit set. These would be the 1 or 2 basically. So we use our occupation map and do plus the LOD. But that's going to be wrong because with MIPS, LOD0 is the highest LOD, but the way we've done it is LOD0 in this case is the highest level of detail. So we need to kind of invert that the other way around. So we'll grab this like this here, right? We'll just be like LOD. Okay. So the maximum number of LODs is data LOD count. Right, then it's just take 1, I think, right? Because it's like a LOD index, so you need to do something like this. So that would invert around the other way. So if you got 0, you end up on 7, right? And if you're on 7, you end up on 0. Cool. So this is the little trick where we do a couple of samples instead of 8. So we repeat the cluster bits. I guess just to give a quick reminder on how that works. This is a slice of a 4x4 bits, so that's 16 obviously. We've got 2 slices in a single bit set of 32-bit integers, and along the XY axis, these are the regions that we initially write to, and then this is propagated into the bit set that comes before along the x-axis, the bit set that comes before on the y-axis, and the bit set that comes before across the x and y-axis. So these 3, like this, we filled in along the bit sets over here in this position for this guy, this position for this guy, and this position for this guy. And when we're sampling it, we're getting 2 bit sets along the z-axis, and we're basically looking at the clusters within here, and then like, because this is all repeated information, right? That's all repeated information. This is the unique one. We can look in the clusters here, and then, sorry, we basically index it so that we only index and land our center position in here. This is where the cluster is we're looking for, basically. So if we're looking for this cluster here, we just check the bits around here, basically, and that will know we're surrounded. If we land our cluster, if we sample the cluster here, what's the way of saying it? If we're sampling for this cluster here, we can look at the neighboring bits here, and so on, right? But it's in 3 dimensions, so we have to go over a couple of bit sets. So obviously this cluster, this information is also in the bit set to the right, at this position here, right? But obviously if you use this one in this bit set over here, you're not going to be able to, it'll be hanging off the edge, and that'll just be if statement code, and it'll be horrible, right? That's the reason why we only, anyway, do that. So this is the magic code that ends up taking those couple of samples and making sure, and telling if they're surrounded. So we basically, so EEE0 means basically a wall of ones that sort of start at this position. Yeah, that go all the way around here. They're all ones. And then 0 obviously just mean, all zeros obviously just mean 0, right, on the bits. So we start off at the top left, and then we just shift it into place. We shift it down a row or right a column, based on where we're sampling, based on this, right? If we're doing this one, there's no shifting that happens, right? It stays in the same place. If there's one here, it will get shift one to the right, and so on, right? And we do that across the 2-bit sets, and we know if we're surrounded by just checking if they're both equal the same. So now, if we know they're surrounded, we clear from our node. Is it our node? Yeah, we'll clear from our node that, hey, this child doesn't exist anymore. And we'll clear that up later because we can't deallocate here. We're taking into account that when we're building this initial cluster tree, that we've built it in a very big array, the maximum size array, and we're building it in this sort of temporary space, and we just copy it out later. So rather than sort of removing nodes and deallocating them, we're just going to do a copy, a persistent copy, and patch it while we copy it. Free the child sphere memory. Is this right? Node sphere memory. That's wrong. It's child node. So if it had spheres, we're going to go ahead. So if it has spheres, we're going to get a new free slot index in the slot array, and we're going to put it in there. That should be safe because all we're doing is, oh no, we are taking, that's not good. In the same shader, we are allocating. So we'll move this to the other shader, I think. We've got enough room to fill up, because the issue is here, one thread can atomic add and allocate a slot within the free indices array, while the other one's subtracts, and then it'll try and read that slot index out. And this one could have stored before it wrote it out or something like that, and you'll read out some garbage index. So this, what we need to do is we need to do that in the we need to somehow say, hey, this thing has got no children. There's a way to do that. Do we just say clear? We'll call it clear. I called the other one clear, didn't I? Yeah, good, that's nonsense. Yeah, something like that. Alright, so you just clear. So we want to say is like, oh, if this thing, wait a minute. It always has 0 there, excellent. So we just go, so we'll free this later. So we're saying clear the sphere array, the memory will get cleared, get sort of freed later. We can't free it here, as we allocate spheres in this shader, and that would create a sort of well, what would it create? Like you're basically, yeah, that would not be lock free. And that would mess with the lock-free nature of the free. Okay, so let's just drag this to the other shader. So here's the make persistent code. It's this very similar shader. We start the leaf nodes and go up the tree. So if the node has children and has spheres, has children or has spheres, keep it. And then you say else if volume. You want to say that, hey, if the node spheres array is not equal to that's sort of like node spheres array invalid, whatever it's called. Volume spheres array invalid. Cool. And now if that's the case, you want to say, we're saying like, node was sort of freed or sort of deleted in the we want to say that this node was removed as it was completely surrounded by other nodes, and a lower LOD sphere was used instead. So let's free these higher LOD spheres, which will not be seen or whatever, okay. Something like that, right? So we're just doing the free here. Right, we don't touch this in this shader at all. Yeah, we're not touching the shader. This is the shader that we're working on today. Cool, so we put that in the right place now. We'll double check it in the next stream when we get that shader up and running. So here we go. So after we've done this code, all in lockstep, right? So all of the threads would have processed all of the children and created lower LOD spheres and possibly marked the children for deletion if the children were completely surrounded by other clusters in three-dimensional space. So after that, we say, hey, if we're the first, if we are the first thread in the right, we're essentially making it so only one thread goes in here. For the cluster. Here we're the first thread for the cluster. visit bits would have been removed. Okay, that's good. Ah. So the visit bits are also being removed because in this child bit set it's 32 bits, and we was only using the low 8 bits to store each child as a bit. But so we also needed to keep track of like how do we traverse up the tree, and basically have a little mask to know which nodes have visited. So again, when we say if you're doing this node, you'll process all these guys, you know, see if you can get rid of their children and whatever, get the LOD spheres. Now you need to go up to the parent and mark in that bit set, that children bit set, that you've visited here. And that goes in the higher 8 bits. And then you basically terminate your thread. But you don't terminate your thread if all of the other visit bits have been set. And if they've been set, you're the last thread to get here, so you can carry on and see if these ones have got any children, and if they're completely surrounded by other clusters in 3-dimensional space, then you can get rid of this guy, you know, put a lower LOD sphere there and whatnot. So you just repeat, it's the way we traverse up the tree. Okay, so we clear the visit bits on this node. What is this one doing? So we're saying, hey, if we've found spheres, ooh. Yeah. If we've got any spheres, we're ensuring we only expect leaf clusters to have spheres at this point. What does that mean? Yes, because you wouldn't have any children. So a leaf cluster wouldn't go through this. So then this would... So we don't even have assertions actually, so that's commented out, right? We should probably... I was going to put assertions in, but we should probably just make it print instead. Yeah, so we'll put that on there. It's called spheres array. There we go. So we've got that lovely print in there just in case. And that'll print out some stuff in the terminal, and we'll go and fix it. So, excellent. So we've found spheres for this node. So allocate a contiguous array of 8 spheres. So we just bump allocate. Yeah, so we take off the end of the stack an index, and that index has been pre-allocated with 8 spheres on and after that index, right? And then we create this spheres array, which is a 32-bit integer, and we pack in the 8 bits the number of spheres. Wait, not 8 bits. Whatever. There's so many bits in there. We pack the spheres count at the top or whatever. Excellent. So when we're outside of this block of code, which means all the threads are here again, we say, hey, if there's any spheres, we copy the spheres all together in lockstep. So you're getting, you know, basically each node that goes through here, there's 4 nodes in a wave. But for each node that goes in here, they'll have 8 threads that come in here. So you pull out their start index, and you just basically copy the spheres over all at the same time from the temporary LDS memory into proper memory. Right, we're nearly there, and we can nearly fire this boy off and see how much it blows up the computer. So now if we have a parent, so we always set parents to this, right? Is that right? Yeah, we set the root to that, and if not, they're always set. Yep. Now, we do the bounds check. If not, we return. Yes, because that means all the 8 threads for that node will end there, and that's fine. Now, we calculate, what is this? The parent-child index. So from within the parent, what is the child index? Yeah, that's legit. Pretty sure it's legit. Yeah. So it's just calculating basically 0 to 7 inclusively, and that, you know, child index is like a sphere index within the in the cluster, the parent cluster. Then, so it's calculating, like, if you're coming from this node, it's able to calculate, given my parent, like, I'm here, right? And you know, it's not that one, it's not this one. I'm talking about this child index here, right? And that's all this code is doing. Then we calculate the absolute index. We get the visit bit, where that's the visit bits. Yeah, so the visit bits, remember there's in that child bit set, there's 8 bits at the bottom to say which children exist, and then the next 8 bits are the visit bits. So we add 8 to the child index and get it up into the slightly higher 8 bits. We OR the bit on to the bit set, and this is the parent, to say that, hey, we've visited here now. And so this is the termination code, basically, we're going to talk about, that I was talking about. Then we get the visit bit set. What is that talking about? Oh yeah, sorry, we get the bits. Yep. Then we get the visit bit set by shifting the bits over by 8. So now we're dealing with, you know, 0 to 7 inclusively in the bit range at the bottom. And we're checking. Yeah, and then we get the children bit set. And then we check and see if all of the children have been visited for that node. And if they all have, we'll carry on and set the node index to the parent index, and then continue. And then this will mean that we can carry on all over again on the parent. But for the threads that don't get to do this, they're going to terminate. Terminate here if we have no parent, or we will not the last node, the last child to reach our parent. Now the thing is as well, yeah, there'll be no problem where there'll be 0 bits, because the fact that you have a parent means that your parent has a child, right? So there's no issues there as well. Cool. So that's basically it all hooked together. It's got to make sure it's all going to be compiling now. Yeah, right, I remember this shade. Yeah, this is the new shader. Oh, this is the shader that we're not doing today, basically. We shouldn't have to clear that, but we might clear it. Shouldn't matter. Right, there we go. Okay. This is gonna be good. So this is everything now, and so it means we can just fire this off. But I'm just gonna take a quick break and get myself a drink. And when we come back, we'll fire this thing off and see if it blows up the stream or not. Right. BRB. Thank you there, Rosmusco. Appreciate it. Yeah, I don't know what happened there. Yeah, I must have kicked the thing as I sat back down, so hopefully I wasn't been going for too long. Alright, so if the stream dies, I'll be right back. But you know the drill. Alright, here we go. Oh, still running. And here it is, here's our boy. So it's taken about 1.3 ms. Okay, to traverse up that tree and simplify. Yes, that's the thing with these shaders. is, so that one's quite a constant. Like we can figure out what the upper bound is for that. But yeah, I'm hoping like this construct leaf nodes one is about 4.5 ms, and we're not even doing much in it. I think the biggest problem is the fact that we're link listing through the nodes at the start. I think we can heavily optimize this one down. Before we do anything more complicated, I want to try and optimize that and just see what the baseline performance is for that at the highest LOD. But now here's the thing. I don't know. Like, there's no way to know how. Like when we, like the only way you can figure out if this works is if we print data information out, right? So we're just gonna write a couple of prints to kind of verify that stuff is happening, and then when we can sort of like, yeah, we're just gonna verify that stuff is happening, and then fix anything that isn't, and then after that we'll just move on to the next shader, because I like we the best we can do from there is basically just try and you know, render using it or whatever, right? Well, we're not going to render using this data structure. We're going to splat it into our acceleration structure from this structure. How's it been, Ross Musco? Have you been up to much lately? How you been? So the first place I like to start is this one here. We're going to print out for every single time we traverse from a node and go to the parent. So we're going to be like, oh, we've gone from this one to this one, and then we're going from So D, so that'd be node index. Yeah, we never have a node index anymore. So I think we use absolute indices in this case. They're going to be quite big though. We can work out from the midpoint cursor. So we do ABS node index. So that's, yeah, you're going towards that one. So do S32. Take away the midpoint cursor. Midpoint cursor. Great, and then the parent one is just here. No need to bother doing any of that. Been good, not up to much. Excellent. Yeah, I guess that's a typical start of the year, isn't it? Just turning the brain back on and surviving in the cold. Hey, have I completed my C compiler? Yeah. Complete as much as we're using it. You know, there's always, you know, you never really finish stuff, right? But it's good enough. We've got vertex shaders, pixel shaders, compute shaders. You know, print. We can print from shaders. We can, yeah, it's awesome. We've got like a maths library built into it. You know, control flow works fine. You know, everything just works all right. There's been a few tiny bugs here and there, but we managed to squash them. Exactly, dog fooding it in this project. That's the plan. So just sort of well, we've written some really complicated shaders already. Although I do think, yeah, we've come across a few bugs in like we come across one bug in the AMD driver, and it was like effort to try and get them to fix it, so I just changed my way my compiler works. Also, another thing I've encountered very lately, and I don't know, I can roll back the commits to it, but on Windows, I noticed like last week that I actually get a crash on AMD drivers when it loads up the shader binary from the shaders I obviously made. And it was before we did the LOD stuff, this LOD cluster stuff. So it's something to do with one of the ray tracers got changed and it crashed. So what's great is we can basically comment out code and fix that at some point, but yeah, I have to go and do that. So we are getting some of these issues, which kind of sucks. And it's just one of those where you've just got to comment out code and see what tiny thing changed and cause that problem, right? And yeah, printf for shaders. Yeah, so we can print out per. Yeah, we can just print out whatever we want. So it's quite basic. So we've got a mechanism. So we've got hacky string support in the compiler. We don't have proper strings, but basically this encodes into an array of 32-bit integers, which is what shaders can deal with. And they're padded with zeros at the end until they round up to 4 bytes or whatever, right? And then basically this gets this string, goes over all those 4-byte integers and sends it out into a storage buffer. And then it just sends out these parameters into the storage buffer as well. It parses, sends out these into the storage buffer as well, each of these parameters. And then on the CPU side, we just throw this. Yeah, I think we manually do our own printf on the CPU side and print out into the terminal. No, that's the thing. We print into a buffer, basically. You can imagine like we take the arguments that we're sending into printf on the GPU, and we put all the arguments into a buffer, and then we just pick that up CPU side, and then do the proper putting it out into the terminal there, basically. So you can actually do that in any. You can't necessarily do it in HLSL because you don't have this. But you have characters in HLSL, so you can do like single characters. But yeah, it's a bit hacky. GPUs. Right. We're going up to the parent nodes, which means that the visit bits are working. Now we just have to multiple threads can go up to the parent, but only at 8 threads, which makes sense happening. Oh yeah. So we're going from leaf nodes to non-leaf node, non-leaf node to non-leaf node. That makes sense because you're going from the bottom of the tree up the tree, right? So, you know, this is a first thing where it's like, okay, that's probably working fine. The next thing I want to check is, are we actually deleting any children, right? Are we deleting a node? Wait, that's not it. Yeah, we want to see if we're deleting a node. So wait, what was this one? This one is saying that we're allocating, we've got LOD spheres, right? Found this many lower LOD spheres, something like that, right? And it would be nice to probably print out the LOD here as well. So we throw in that node index. We throw in the volume cluster location LOD. That's node.location. Then we put in how many. Right, and that's another good one to have a look at. So we want to know if we're actually making any low LODs spheres, and the answer is no. So there's something wrong there, which sucks. So we'll leave that one in. Yeah, awesome. So something's wrong. It's not going into here, basically. So I want to print out, like, you know, child node. We'll just print out something like this, right? Well, yeah, we'll just print out like child node index. Just something like that will do. So we're not even getting into there. Very weird. Do we get into here? Right. Child node 0. That's the root node. I'm very confused. Ah, we're indexing into this child node array wrong. I remember we messed with the so we don't use the absolute index, right? We don't use the midpoint cursor plus the offset to this midpoint cursor in the array to that, which makes an absolute index from here or whatever. We don't do that. Instead, we just use the absolute index from here to index into a different array. And the reason is because this array can actually be smaller because it's a little temporary array that we only use while we're building, and it stores all the child indices in it. And we have way more leaf nodes because at the highest LOD, right, at the higher levels of detail, you have more information, right? Whereas in the lower levels of it, whereas in all of the non-leaf nodes are in the lower levels of detail, and these will go. These are a positive, right, from this midpoint cursor. So when we index into this array, we've just basically made it so it's just got enough for all of the non-leaf nodes that can actually have children. So we, rather than using, so we actually do need to update node index in that case then. Right, so that should fix that. Hi, how is printf on GPU works? Are you writing some string to the buffer? Yeah, that's basically it. So we're literally just like, so it only works as well as it does because I've got my own custom compiler. But there's nothing stopping HLSL from doing this. But they don't support it, right? And in GLSL, I think they've got some form of thing in GLSL that means you can possibly do it through some extension. But yeah, the way we do it, let's not go into the thing. So this is just stored as an array of U32s in the SPIV binary. And it's just a regular string, null terminate string. So all I do is I have this macro, which goes over each of the macro arguments. So the first macro argument, it writes out to the buff. It knows it's an array, and writes out that array of strings to the buffer. This one, it knows it's like a built-in one of the. It knows it's one of the primitive arguments, and it will figure out which one it is. and it'll write it out to the buffer as well as an array of bytes. And then we just pull those back out CPU side, and we get the number of arguments, and we can know sort of like the size of each argument. That this one's like, I don't know, 12 bytes or whatever. This one's 4 bytes, and the next one's 4 bytes. And we pull that out CPU side, and we just like print out to the terminal as if it's like a you know, yeah, basically. I think I throw it through. No, I don't throw it through printf. But yeah, something like that. All right, so this should fix it. So if the stream dies, I'll be right back, but it should be right. Nope, stream dead. Yep, got a GPU crash. So right, that should be better. Okay, get the music back, because I'm sure we won't hit that again. Right. Get a Stone Rebel back on there. So I should be back, right? Good. So, right, what is the problem? We've got to check over all the possible. So it was going up all of the nodes successfully, right? The link listing was happening successfully. Oh my days. There's an infinite loop. So let me check. I know what the issue was. Let me just double check this is correct first. So we moved this out from, this was outside the loop, and we moved it here, and it's causing the bug. I'm pretty sure about it. So it's that one plus that one. Yeah, this one's fine. All right, here's the bug. We keep visiting the same node index, and therefore it never ends. Rather than, so we use the absolute here, ABS. Where is it? This one. You know, let's move it out of the scope as well. We need both. ABS. Oh, we've already calculated it here, so just pass it through. You know, makes sense. So yeah, the end of the shader, I was not updating. Wait, which one was I doing? No, I was updating the node index there. Ah, so maybe that's not the problem. Was that right? Right. So nudge with sound cable, sound device disconnects, reconnects, causes problems in OBS. Right. So before we came back in, yeah, this was there. No, see, I don't remember what it was like when we came back in. Whoops. What did I do? Yeah, I changed it to this, didn't I? Because I remember grabbing that with my mouse and putting that there, yeah. Then I moved that and I was like, yeah, we set both. Okay, so that is the fix. So we could do this piece by piece. But what other accesses are we doing, right? So we access the child node. This one is correct. We're accessing the spheres. They're allocated right, so that's safe. Yeah, I'm pretty sure it's all pretty safe from here, so hopefully it doesn't crash the stream again. If not, we'll be right back. But I'm pretty sure that's it. Right, fingers crossed. Oh yeah. Right, interesting, we should be hitting this. But, this is great. So we're printing out tons of stuff now. We just got to disable the ones that we... Let's disable the error one. This one is saying, hey, we've found some lower LOD spheres, and we're allocating them, right? And I think I saw that message. There we go. So found some LOD spheres. Found 0 LOD spheres. What? There's some weird buffer overflow going on. Or something to do with the way the arguments were written out. Oh, at you, that one. Right, I put too many arguments out. So it was using LOD. Right. It's fine. Okay, so LOD 6. Yeah, made some lower LOD spheres at LOD 6. I don't know if it made any more. We could put an if statement around it to say, hey, if you're less than 6. Probably filled up the buffer very quickly. There's like tons of these nodes. Let's try it again. Right. So at LOD 5 we've got some as well, right? They're shrinking down, which is good. So that means the MIP level thing must be working, right? This MIP, the low level MIP texture of the occupation map, where each bit is a cluster. So I can check the neighboring clusters if they exist. That appears to be working. Working correctly, we don't know, but it's given us results, right? So I think we'll end up stopping at a certain LOD, because yeah, we might not get LOD 0 or something like that where they have LOD spheres. So LOD 3 and 4 are starting to... Okay. Computers. Computers. NeoVim Emacs. I'm using NeoVim. It's alright. Does the job. Hey Master Agent, it's been a while. How you been? Welcome, welcome. How's it going? Right, it's just in less than 3 now because we've seen 3 and 4. Okay, this is great. We've found only 2 of the nodes at LOD 2, right? LOD 0 has got 1 cluster. LOD 1 has got 8 clusters. LOD 2 has 64 clusters, which means, right, it seems like it's working fine. And they each have 1 lower LOD sphere in there, which means, let's draw it out so it'll make sense for you guys. Right. So we have essentially this sort of volume which is 256 cubed, right? Filled with spheres. At the highest LOD they're like proper at the 256 cubed, right? So when we've painted down this sphere or this ellipse or whatever, and we're filling in this ellipse with spheres at the LOD that was put down. So we use the highest LOD, so we're painting them down at the highest LOD. Then, but what we've managed to do, right, is we've kept the higher level of detail around the edge, because that's what you want, right, is the high level of detail around the edge. But what you want to start doing is saying, hey, this cluster of spheres, or this cluster of spheres is completely surrounded by other clusters of spheres. So what we can do is we can replace these with one bigger sphere, right? And so on and so forth to the point where when you have, like this is, imagine these are clusters now. It's a little bit confusing the way I'm drawing this. But then this would just be maybe collapsed down into a bigger one, right? Very crude idea of what's going on. So we're not at this LOD, right, where we've got 8 clusters of 2 by 2 by 2 clusters, each with a 2 by 2 by 2 of spheres in. Instead, we've got a 4 by 4 by 4 of clusters with a 2 by 2 by 2 of spheres in at L2. And there's 2 spheres which are sitting there, probably in the middle of probably in the middle somewhere. And they get in one lower LOD sphere, which makes me believe that the code is working just fine. But that we can't see until we actually render it. I can look at some things on a grid, but that will kind of be boring. It'll just be better just to see it, right? So that's cool. I like that. That's really great. So we'll take that as a win. Which means we can move on to the next. Preparing for the next shader. Oh no, the writer decided to eat all my memory as a join. Can't hear a thing. Oh, hey Master Agent, how's it going? I was just asking how you were. It's been a while. Good to see you, my friend. Did you have a good Christmas break and New Year? So what is the next shader? So there's actually a very easy shader, and this one just prepares the volume that we're gonna. So what we've currently been doing is building in temporary space. So we've got many pieces of memory, but effectively there's a chunk of memory. There are chunks of memory which are only for building these volumes in, and then we heavily simplify them, which we've just seen happen, and then when it's done we're going to copy it out to a persistent place in memory. So technically we need to allocate some memory and then use that and then copy to that new allocation. So basically we need some form of like GPU allocator, but we don't really need it right away. The best thing, the thing that we want the most. Right, there we go, I'm back. So sometimes this happens, you know? Saw an amazing Backrooms game made entirely in dreams. And thought of you. Awesome. How was what is a Backrooms game? Yeah, there's lots of interesting stuff happening in dreams. It's just insane. People stuff doing it. Awesome, thank you. Oh, your audio. Yeah. Yeah. I was asking what is a Backrooms game? I've never heard of it. Christmas was good, but extremely cold the week after. Yep. Well, it's cold right now in the UK, it's for sure, isn't it? Lots of work for the past months. Studios I'm working at has a game releasing next week. Wow. That seems to be awesome. Congratulations on the release. That's really cool. I've not released a game yet, so I don't know what that's like. Can imagine it's, putting out tons of fires and stuff. I can imagine that. Um, but yeah, things are going very well. It's been chilling, um, home, you know, looking after the baby and spend time with my family. Um, Working a whole ton. Like this past week has just been absolutely crazy at work. I've just been going full ham on some task because I want it to be like really good, but also I don't have a lot of time, so I've just been going all in on it. Um, and what else? I'm also preparing to go on holiday in February. Whole of February, going to be away. Going to be going to Australia. Um, so it's going to be awesome. And yeah, in terms of this project, we've been doing some big, complicated LOD clustering system. We're getting near the end now, where we can start to actually see things, and then we can play around with trying to make it better, trying to improve a few little things about it. Maybe we can test find all the edge cases and be like, is that how do we want this thing to behave basically, and fix that. So yeah, it's all going good. And then I can move on to some other rendering thing. Lots of other past months. Okay, yeah, first that backrooms. Right. Okay, good. Have a little gander. Let's try to breathe water. There we go. No, I've never seen this. This is weird. Interesting. Okay. Mm, fair play. Uh, oh, there's my editor. So basically, we're just gonna allocate Like, so eventually we need to write a little heap allocator on the GPU, or a free list allocator, right? On the GPU, because we're going to have a variable number of nodes. So we just need to know how many nodes we're going to have. Excuse me. So where's the burger? The globals. Here we go. So in the globals we've got some volume constructor things. So we've done. Oh, yes, the leaf nodes already got made ages ago. So we can modify these counts, right? So let's figure this one out. So if we can modify these counts, we can know how many we need by the end of this shader, and maybe I can get the shader ready to sort of do the heap alloc. So where's the delete? Here's the delete of the node. So for this one, you just need to know, like, hey, if this one is a child node, wait, 2 seconds. Right, so we don't do any allocation here. Excellent. So what we need to do is we need to say, right, so if this child node index is negative, then it is a leaf node. That's got deleted. Yeah, so atomic add it's always subtract, sorry. I've got its counts and not offsets or whatever. Then the non-leaf nodes. Now, yeah. And then this code is simply, decrement the sort of leaf or the sort of nodes count. Right. So that's all we're doing there. So now when this shader's done, this refine, we can look at those two and know how many nodes we actually need, and we can allocate that. So, man, it'd be pretty cool to write a free list allocator, but we don't need to do it right now. So the point is, we can just use like these globals, and when you reset the volume, so it's like so we allocate this volume index on the CPU side, like a typical pool allocator or something. We get the midpoint cursor, which would be the leaf nodes count. The number of leaf nodes will be here. And then the non-leaf nodes. So remember, this will be to do I just realized. So this would be like alloc. Yes, you might be able to use multiple threads in here to do some sort of really fast free list allocator where it searches over all the spaces. Maybe before we do this, we defrag the memory or something, so we can just take it off the end of the array or something like that. Yeah, that would probably be the best approach, maybe, because you'd have to defrag anyway. So yeah, we'll figure that one out. But anyway, you'd be like allocated start index. Yeah, and it'll be that plus this. Right. So we need to call this volume reset basically, and this will set up the volume, which is being created on the GPU. Take a look at this. And the dark mode is, oh, there you go, good. Published, right, middle of, right. It's had quite a good number of plays. Yeah, I think that's one of the Dreams games. That's a different one. It's one of the I forgot who made that one. That's kind of creepy. Pepe. Right, so volume reset. What do we need here? Volumes and the cluster nodes. Do we need the cluster nodes anymore in that one? No. What is that? Hang on a minute, I have just realized something with the... With the globals buffer, we're not doing any sync code on it. So I might just be getting lucky with that. Oh. Yeah, we'll think about that. Right, so we're just going to fill in this one. It's be quite easy to fill in. Yeah, we'll investigate that thing. What is going on? Right. So we fill in the clusters there. We know volume index, this would be like to do. Right. To do pool allocate. That one. And it's like grid dims or whatever, and that comes from data volume. Grid dim. We didn't store the grid dimensions in the... Right, maybe they can just come from the GPU. The GPU can work that one out. We might need to know that information, I don't know yet. Okay, so we need to read write, or write only on the cluster nodes. There we go. So that's kind of something, right? Let's get the volume reset in there quick. Right, so I'm glad we didn't have to spend time on that heap allocator and we can just move on. That's good. It's not indirect. we're launching one by one by one. And then what the hell is this? This is volumes. It's not the cluster node, it's the volumes. Buffer ID, fantastic. Right, so that'll launch just fine. But the thing I'm a bit concerned about is all these shaders are using this sort of globals buffer, and we're not really synchronizing on those. Yeah, we're not really synchronizing on that global buffer. So what we should do is make sure we get that right. Because, well, I guess it's always just going to be, like, you'll put the barriers, yeah, but they could be flushing, yeah, you need like some cache flushes basically. So we should probably get that right. So I have all of these buggers. Here it is. Right, so we need to say graphics global buffer ID. This is it. So in this shader, relist one, we do a read write. What else? We do write only in. Right, you do write only in cluster constructor reset. What is this shader? Construct leaf nodes. This is going to be a read write, isn't it? Yeah, read write. Construct the tree. Read write on that global buffer. This one, the indirect arguments, it doesn't use that, right? When it generates the indirect arguments, very short-lived shader. It does use it, of course, it's read-only. So that synchronization never has to exist. I put it there to say, hey, we need to wait for this one, but not thinking that, hey, we're actually using a shared buffer and that's the global buffer, right? It makes tons of sense. It's read write actually. Whoops. Make sure that's right. There we go. So the occupation map gets cleared. This one is the generate the occupation map. That one must use the globals, right? Read only there. What else does it do? Just read only. Occupation map. Cool. Downsample. The special downsample, it doesn't use it at all. And the refine, this mutates it, right? Yeah, we mutate it. So it's a read write in that new refinement we've just done today. Excellent. Now in the reset, which is the one we're gonna, this one obviously does a read only. So reset the volume, read only. Oh yeah. Okay, so let's launch this guy. We'll see if the GPU wants to crash or not. So these grid dims, I don't know if we want these. But for now, just write to do label on that one. No, my compiler, no. Where the hell did it do that? What did I change? But it was just compiling just fine. Like, what shader did we change recently? It's this one. I know it is. 842. We need to take the address. Yeah, that's not a good issue, is it? There's not a pointer type there. So what thing do we get there? Right. Yeah, we haven't ensured that that's a pointer type. So it does fail in the syntax tree in this case, but it still fails in a very bizarre way. That's not good. It really isn't good. Right, let's see if this works. Right. Okay, so we end up resetting the buffer, obviously. Right, there you go. Good. The next shader to hook up is this make persistent. So this one is quite basic. It just copies that persistent place in memory. What do we need here? The volumes is read write. The clusters, the cluster nodes. Yeah, I was thinking we was going to do two separate ones. So a read-only one. There's source and destination. You want the sphere free indices, the occupation map. Why would you want that? Need that. Where do we don't use that at all in the make persistent. Yeah. So we delete the occupation map. The spheres. We don't use that either. We're not writing any spheres. We're just deallocating the ones that are not needed anymore. Yeah, so that should all we need to do from there. Yeah. So to launch this one, let's copy these. So I'm going to launch this shader. We need the volumes. We need the destination nodes. That's in a separate array from the ones that you build in. So volume cluster nodes. We see we haven't got that buffer yet. We'll get that done in just a second. It's this one. So there's an even bigger buffer which has all the persistent volumes. Sorry, all the persistent data for the volumes. in a different buffer somewhere. And when we're temporarily building it, we'll put it into this one. What else? And the free indices. Awesome. So I just want to go ahead and make that. This one here. Shouldn't be too bad to make. So we've got a volumes capacity. There's also some other things we've got. Max 4 volumes. The max number of 4 volumes we want to support. Times by number of spheres, excellent. So something like this. So max number of, yeah, we should probably have that written down somewhere. So the volume nodes capacity. This would be a good one. So this would be max non-leaf nodes plus max leaf nodes. So that'll get you the maximum you would ever need for a volume. And then we'd multiply by the number of volumes. Now that'd probably be quite a big number. So we might have to tweak around. Tweak the numbers a little bit. So this is gfx dot, and then we delete that there. Okay, so let's just quickly patch this, and I'm going to do some quick maths about the numbers. Oh, wrong one. Destination. Oh, that's already good. Yeah, let's do the sync code now. Synchronization. So it's read write, or it might be write only. I don't know. Probably doesn't matter that much. Are we mutate? How are we using the globals? We're loading, adding. Yeah. Right, so read write on the global as well. There we go. So that'll be read write, read only, read write. Technically you might have write only on the buffer. Let's just have a quick, let's do it. So we make persistent. We're doing our copy. It's just copying the node. Yeah, it's probably write only. Oh, there we go. Sweet. Oh, destination write only, read only on the source. Oh, where's the volumes? Read write. Volumes buffer ID. Cluster nodes. So destination source. Excellent. Oh, and that's got to obviously launch the right shader. How many of these are we launching? So you need to launch as many as you have leaf nodes, which we don't know. So it has to be indirect, which means we're better off using this one. Yeah, it's the same. What we should probably do, we'll give it its own one. So say cluster make persistent volume, make persistent, whatever, right? Args. So that's in the global buffer. Just need to get those in there like that. So these are the dispatch args. We need to fill those in on the GPU. Luckily we fill them in the same place as these guys, very easy. It's actually a copy of the one above. Technically we could just reuse the same args, but then it'll just be a little bit less readable. So we're effectively launching based on the number of leaf nodes that we have, divided by 32 rounded up. And that's it. So that should launch, since we're doing one thread a node and 32 across the X, right? In a wave, right? So cool, so we'll go over this shader in just a minute. I forgot what I wanted to look at now. Where is it? This is completely the wrong place. Yeah, here we go. Oh yeah, I wanted to see how much memory we're allocating. I think we got far too many. And also the full buffers doesn't make any sense. Yes, right. I know what's going on. It's gonna be good. So let's explain. Full volumes. Okay. So this max full volumes is like, this needs to be some number based on how much, I don't know, GPU memory there is or whatever, I don't know. But for now it's a constant. So the basic idea is of a full volume this is also wrong. A wrong thing to use. It's correct, but it's wrong to use. This means we're going to allocate way too much memory. So by the time so think about it this way, right? You've got this 256 cubed volume. If you fill that with spheres, there's a whole load, right? There's this many. There's 16 meg. Yeah, there's 16 meg worth of spheres, right? So in our sort of temporary building space, we have this number multiplied by the amount of memory we need per sphere. You know, and a cluster is 2 by 2 by 2 of spheres, which means that's 128 cubed. And we multiply this number by the number of clusters, and that's the most we need to construct this sort of volume to build inside this space and then simplify it. So the key word to that description is simplify. So everything's actually going to get simplified. So realistically, on the edge, you're going to have, there's 6 faces, right, in 3D. So realistically what you have is 256 squared multiplied by 6 faces. That went wrong. So there's that much, there's that many spheres that fill the volume around the surface. But we actually have some on the inside as well. So what I think is practically safe is there's plus half more of this, or there's 2 times this, and that's a way less number than the number that we have here for the max number of spheres, right? So, and that'd be realistic, basically. If you've seen the movie Waterboy, then you might be interested. Oh, then this might be the best thing ever. That's a good film. I remember watching that as a child. Then you open that in a private window. Oh, I forgot this scene. I did not realize. Right, it's this one. I did not realize it was dressed up as a lady. I forgot this one. Oh my days. Right, let's jump this one up. Negative 26 when it. So this is definitely like, yeah, definitely like the wrong, probably AI. No, is it not AI? It's 9 months ago, maybe. It's not the same script, is it? It's been a long time since I've seen this film. It is AI. It sounds like a familiar script. Yeah. Oh yeah, it's the right same script. That's a good one. Yeah, it's good. Alright, it's not blast story holes with music. Let's turn it down a bit. Right, so someone said it and the AI fixed it up. It was good. So we could just multiply it by 2, and that'll probably be enough. Like that's way less memory. See, this number is 15. That's not even right. That's off. Yeah, yeah, I did 250 cubed there. Right, anyway. So this is already like 16 or more less, right? So this is great. So we can just say this is 786 432. So this is 256 squared times 6 times 2. That's what this is. So we want to put this as like max volume spheres count. So we want to say this is like a rough guess. Like rough guess, 6 sides of a cuboid. Multiplied by 2. Right. You know, should be alright. So that means when we're doing, here we go. So if we're doing nodes, right, it would simply be, it would be half that number, wouldn't it? No, it's half across every dimension. So just divide by 8. No, we want to do a similar thing. Volume nodes. But instead we'll do 1 to 8 cubed. Yeah. So 1 to 8 cubed. Sorry, 1 to 8 squared, I meant. Multiplied by 6 for 6 faces, then by 2. There's roughly divided by 8, I think. 196. So we times this number by 8. What do we get? Oh no, wrong one. Alright. So times it by, is that 6? Oh no. Yeah, so times it by 4, we get that number. Right, okay. The upper number. Right, so that should be a good constant to work with. And that means we're not allocating way too much memory. Cool. So we're going to start up to like, I don't know how many we're going to have, but if we just look at the numbers. So 7, 8, 6, 4, 3, 2. So we've got 60, say if we had enough for like 64 of these volumes, that's 50 megabytes, which is all right. So let's scale this up a little bit more, right? So it's 7, 8, 6, 4, 3, 2. So say if we did, okay, I should have just multiplied the other number, but that's all right. So say if we had in memory, yeah, so we had 1024, that's going to shift it up, isn't it? So that'd be 700, that'd be 800 meg of memory. Which is not bad. So that's like 1,000 volumes in memory, maybe. Well, plus whatever, so that's just for spheres and nodes. And that's for 4 volumes as well. Okay. And we won't have 4 volumes all the time. And that's an overestimate as well. So I think we can pull off having an yeah, I think we can pull off having a very high number of volumes, unique volumes. No feed will be filled with AI. That's why I use the incognito tab. Well, to be fair, I don't have my YouTube signed in, but yeah. If I did anyway. Actually, it might be because Google... Yeah, it won't be as bad. I swear sometimes I search for stuff on like other websites and it'll show up in my YouTube. Well, I'm using spheres, by the way. Is it easy to go like do light bounce checking? Yeah, so the thing is about a sphere, the Raver sphere is quite cheap. But I think we're actually going to do ellipses. But we're storing them as spheres in this volume structure because we're storing them as spheres at the moment, but after we get it working, I want to try and store them as ellipses in this volume structure. So what this volume structure is it's basically just describing some form of 3D volume of spheres that's been simplified, where there's only high detail around the edge of the volume, right? And yes, there's only high detail around the edge of the volume. So the idea is we then, when we want to try and render this volume, we first check if the volume is like in the screen. If it's not on the screen, don't render it. We then, if it's inside the screen, we look at all of the leaf nodes. I think the leaf nodes, not sure which way around it is. And then we're going to throw it into, we're going to then bin them into screen tiles after that. That's the plan. Yeah, we'll bin them into screen tiles basically. And we should have heavily reduced the amount of nodes. So what a node is, that's the other question, is a 2x2x2 of spheres. That's all it is. So instead of a 256 cubed, there'll be 128 cubed nodes at most. But we will be reducing that number after we've built it and condensed it. So hopefully, this is the hope. Hopefully we don't have, hopefully it's quick enough to take these from this LOD cluster tree and basically take those spheres out of there and bring it into view space, right? Bring it into the camera. So you have like a camera, like a view frustum. You'll basically go over all of those spheres and just place them in the world at the appropriate LOD they need to be. Just something like that. And then we'll ray trace against them. So they'll be binned on screen space tiles. So each of these tiles will get an array of spheres where they tell you their location in view space or whatever. And then we render them. And then we go over and ray trace against all the ones that are sort of in that tile for the pixels that it goes around. So that's a system we already have in place. We just got to fit it into it basically. So yeah, it's like a mesh, but except for it's gonna have, we're gonna be able to animate it a bit. Like the cool thing I want to get working is all of these spheres can sort of like move around and feel organic. So we'll have like some bones or whatever that sort of affect this volume, and you'll be able to take these spheres and, you know, multiply them against the you basically skin them, do like a skinned, you know, calculate the transform to take it from the sort of the local space into the view space and make it skinned, right? And so we should be able to get some really like, so you'll get the sort of skinning, but then we're able to add some sort of velocity to it and get some sort of natural, organic sort of looking movement apparent, or hopefully that's the plan. Not sure how it looks until we render it, so but that's the dream, right? Yeah. So right. I guess we can quickly go over the shader and just see how it works. So this just copies the persistent memory space, that's all it does. So it starts off all the leaf nodes and goes up the tree. That's basically how it was in the previous shader, it's fine. There's the midpoint cursor. The leaf nodes are negative of the midpoint cursor. Source, midpoint cursor, yes. The bounce check doesn't make any sense anymore because we've mutated this. so we need to get rid of it. The safety check, like we've already done this, so it's already safe, right? At this point, we've already. Yeah. Oh, it's annoying. Unless we put it in a different. Part of me feels like we need to put them. It might be better. They'll do something like that. We said we have a final. So essentially we're making it kind of assigned to itself, but slightly renamed. Yeah, slightly renamed. So this one's going to be final and final. So then when we do the... Here we go. When we do the refine and generate the lower LODs, we use final leaf nodes count and subtract from that. Then this one, volume reset, the final count, final count, final count. Excellent. So that means we can still use have the information here and do the safety check just in case. So I like that a lot. Get the ABS node index. We moved that in there, didn't we? Which means at the end when we go up we need to do both. No biggie, we'll get back to that in a minute. So we go over all the nodes. We get the parent-child index. This is 0 to 7 inclusively. It's the sphere or child index within the parent node that this node represents. Since this is a higher level of detail node, it has a single slot in there, in the parent node. Yeah, it's round thing. So that's all that one does. What's be good enough? So then this gets the sort of safety check on that. Right. Generate that. Oh, good. Why do we need that in the end? Huh. Because you're doing... Right, that's the same thing as up here, so realistically we can just copy that. Yeah, I think I needed it there initially because I was doing some patching and then I realized I need to do some patching because I'm copying it out or something dumb like that. Anyway, right, so now we can just delete that. So what does this code do? So while we're doing the copy, we're basically saying we want to keep this or not. So saying, hey, if it has any children, or wait, is that right? Because you would have come here from. You need to do the mask because the visit bits. Yeah. You would mark down some visit bits. Oh, there's something sketchy with this. Okay. Yeah, there's something a bit weird with this one. So we've got the low 8 bits, which store the child bit set. This next 8 bits store the visit bits. What we probably want to store is the new bits in the 16 to 24 bits of those, and then move those over before we do the write, and then store it in there, something like that. Because that's not going to be... It's going to mess up with the traversal code. Or traverse up the tree. So what we need to do instead... Where's the bit where we clear the traversal... So this is the previous shader. Remove visit bits. Just to check. Right, so the visit bits have been removed, and we want to pack it in the higher one. So I want to pack... there's a... where is it? Children bits. Right, here we go. We need more. Right. First set of 8 bits are children. The second set of 8 bits are the children that have been visited. I've done it in 2 shaders as well. Once in the refine, right? Oh, and the make persistent. The new one that we're doing. And the third set of 8 bits is the final set of children. So there's a shift. Right, so what we're doing is we're packing these. So pack the final children bit set in the higher bits. Something like that. And then we'll fish them out later. So in that make persistent code, so this doesn't mess up with the traversal. Wait, we need to remove we need to all that, then we need to and out the 0x 1 byte, 2 byte, 4 byte. Yeah, so you want to remove the, what are we removing? Remove the visit bits for the next shader. Yep. So the visit bits allow us to sort of traverse up the tree in the shader code. All right. So now all it means we have to do to send if it has any children. This is where you want to get out the final so it's that shift right cluster children count times 2. So then if that's non-zero, or if it has any, okay. So when we pick up a node, we say, oh, if it has any children at the end, like in the we've decided, hey, it has some child nodes, or if it has any spheres, we want to keep it. So then we're going to copy this to persistent place in memory. So is it a leaf node? Check the final bit set. If it's a leaf node, then we allocate to the left of the midpoint cursor. Then if it's not, we allocate to the right of the midpoint cursor. And then we calculate the final destination index. Before we finish, we update the children bit set with final children bit set. Excellent. Oh yeah. And then poke that into the new allocation slot. I just realized that we need to these actually needed to be 0 the whole time. So I want to stick a comment here. This is going to be these are bump allocated. Bump allocated from in. These are used to bump allocate. Right. So that looks really good to me. Don't see any problems with that. This one is the... Right, so we're saying, hey, if we don't want to... We're saying, hey, if we want to keep this node, do this. But we don't want to keep this node, and it has some spheres. Then deallocate them. And I just got reminded there was a print statement that ran and we didn't check it. Let me finish checking this one and we'll go back. So yeah, we basically just, this node was removed as it is completely surrounded by the nodes. In 3D space. And a lower LOD was used instead. So let's free these higher LOD spheres. And here we're saying, hey, if we have a parent, go back, do the safety check, get the parent-child index 0 to 7 inclusively, right? It's one of the spheres in the lower level of detail. Get the parent index, get the visit bit. Yeah, same code as earlier. Oh, this thing. I forgot. Source, destination. Source. So that's not read-only then. It's read-write memory. That's fine. No worries. What else could be an issue? Yeah, then if the visit bit exists and with the last one to visit, go up to the parent, carry on. Excellent. I think we'll put a comment down as well. Right, so hopefully that compiles. I do remember we had a... Oh, where's that midpoint cursor? Ooh. There we go, cool. So I kind of want to make sure there was this print statement that was happening, and I want to verify whether that's correct, this one. So in the previous one where we refined our levels of detail, so we did all the simplification basically. This error happened here and I don't know. Oh, we meant to say that's not equal. Right. So what I want to do is I want to not execute this make persistent just yet. We'll give it a go. Before the stream ends, we'll definitely give it a go. But I want to run this to see if that error pops up in the thing. This shouldn't crash the GPU, it should be fine. It won't change much. Good. Excellent. So we're not seeing the print actually happening anymore. It's because this if statement's the wrong way around, right? We're saying that if there is any spheres here, like, because that would have basically made we would have leaked some memory there, because we would have just allocated more sphere memory. But yeah, I had it the wrong way around because it wasn't a assertion, but if we just turn it around the other way, you'll get the error. There it is. Cool. So I'm happy with that, and super great, and that works. So what I want to do now is launch this make persistent shader, which just does the copy from the temporary space which we've been building in and copies it into the persistent space. And this is the final shader until we have everything just in memory, and we can now take it out of, we can now basically put it into the ray tracers that we've already got, and see how it works, right? So let's, hopefully this make persistent works, and then we can test we can check render dark, make sure that's fine, and then we can in a future stream wire the whole thing up and just see what it looks like. It's been a lot of shaders. Let's get this to work. Volume, cluster tree, nodes count. Yeah, making sure that midpoint cursor is in the right place, right? 0 plus that number. Good. Okay. So, the stream could die, if so, I'll be right back. But it should be alright. Go. Oh yeah. So it does run. Make persistent. That's actually a nice quick shader. Which goes to show, traversing up the tree the whole way and doing a bit of copying is actually pretty quick. 0.15 ms. And that's going up a tree which has way too much information. Right, you're traversing the full tree at this point. So I think then, so this is basically verifying for me that it should probably take half this amount of time. Okay, maybe this time at worst, because we might be copying more. No, it will maybe take half the amount of time as this shader, because this one goes over. Oh wait, I've got to cancel the shader now. The program. So we've gone and filled in this space of 256 cubed of spheres, and we've filled it up with the most amount of nodes you'll ever be traversing. So there'd be about, sure, we've done the simplification, but we've still left the nodes in place, and we're going over them again from the. Wait a minute, I haven't verified this is correct. But then again, this code, yeah, we have to just check the number to make sure that this is fine. Sorry, these numbers in memory. We can check that in a second. But yeah, where was I going with this? But yeah, we're traversing up the complicated tree and only copying out the nodes if they're actually used, right? So we're going to have way less nodes when it's simplified. So ideally there would be less traversal. Less leaf nodes, less traversal, all that good stuff. So let's go into render doc and just see what... I haven't got the latest render doc. I really need to get that because we found out the version I have has some bugs, and it's probably because it's a custom build one that I've done. Right, it's just we've got a capture. Let's go and get the information. So it's this one here, right? Maybe. Make persistent. Okay, so after make persistent, what is it that we want to get? No, I'm on the wrong one. Right, volumes. Oh boy. Right, here's the memory. It's all garbage except for the start. So we need to make ourselves a new node. Oh, I didn't save my... Dude. Not that I... Still though, I didn't save my thing. Where's our volume and GPU memory? I didn't write this one out before, by the way. There's a different one I wrote out. So we just want to know what the midpoint cursor is. What the crap is... Truly... Huh? Yeah, so we just want to put a few U32s down, basically. Strut volume. Wait, how many U32s we've got just in an array? 1, 2, 3, 4, 5, 6, 7, 8, 9. Not a good number, but there we go. Oh, I need to put U in. Okay. Midpoint cursor got set to something, this number here, right? Leaf node star index, that one, I don't know what I'm doing with that one. I thought that shouldn't exist, to be honest. We should really delete that. Leaf nodes got set to 1. There's one leaf node. And there's that many non-leaf nodes. Something is fishy there, doesn't feel right to me. Let's double check that one. So why is it allocating? Is leaf? No, something's wrong there. So you're saying, hey, if this has children, it's the other way around on it. I still think that's weird. But we'll try that one again. Okay, it shouldn't crash, but there it goes. Right, let's give that a run. No, it's still running. Let's relaunch. Don't save the capture, please. Nice. What is this one? Make persistent, excellent. Pipe, compute shader, volumes, view the contents. I need the thing again. It says 8 floats. UN array of 8. We're still at 1. Oh no, we haven't. We've got 18 now. And then 1 non-leaf node. That doesn't make any sense. Okay, it's definitely something fishy with the final copy. We're gonna have to debug this. Yeah, I don't know what's going on exactly. You stopped using them a long time ago. Yeah. Yeah, I don't know. I do really like the idea of there's something about you know, purely text user interface that sort of like does, you know, is pretty cool, right? But then when you actually every time I've tried to program for a purely text terminal interface, the restrictions of, you know, they seem like okay at first, and then you just realize how limited you are in the amount of stuff you can actually do. Like, you can't have different size text. You can't have, you know, images or something like that, you know. Things have to be aligned to cell size. So, yeah. But I do get a lot of joy in, you know, booting something up, seeing it visually, and programming for that. Like, yeah, I was doing like just, you know, server-based programming. I'm not sure how long. Oh, I still like to program, but yeah, it won't be as pleasing, I guess. Yeah, I do like that visual feedback. Yeah, so there's something fishy going on here, although we're really close. So it's also a very basic shader compared to the other one we just did today. So I'm pretty sure next stream we can get this thing, verify that it's working. And then hopefully write another shader which bins into some screen tiles. Should be proper cool. Right. So next stream will be Sunday at 6:30. Yeah, 6 p.m. GMT. That's what we're doing. So trade lost miles, right? Yeah, so thanks kind of everybody. I'll see you all in a future stream. Good progress today. Much further than I thought we would. So hopefully within the next stream or two we'll see stuff on the screen, right? See some spheres and see them at different sizes as well. So it's gonna be interesting. Oh, jam on toast. No worries, man. It's cool. All right, have a good night. Catch you later.